Section 24.2. Describing localized bonds using hybridization for methane, ethane, and ethane. So first, let's look at C2H2, ethane. This is the electron configuration of carbon. This is the atomic orbital diagram of carbon. So now we promote one of these two electrons to here. And then we have one electron occupying each of these four orbitals. Now we're going to have this one and this one be mixed to create two sp hybrid atomic orbitals. And then these two are still just p electrons. Now I want to emphasize this. After hybridization, these two are still atomic orbitals. They are not molecular orbitals. They are hybrid atomic orbitals centered on the carbon atom. Now I'm going to give you the wave function of the two sp hybrid atomic orbitals. It's simply 2s orbital plus 2pz orbital and 2s orbital minus 2pz orbital. The square root of 1/2 is the normalization factor. So if you look at side A and side B, you can see the coefficients in front of 2s and 2pz are either the same or the opposite to each other. Therefore, we can tell each of these two sp hybrid orbitals contains 50% of the 2s character and 50% of the 2pz character. We can prove these two wave functions are normalized and orthogonal to each other. So first, let's prove this one is normalized. We take the integral of the squared modulus of this wave function. We do this derivation. The result is 1. It's normalized. Again, this 2s is normalized. 2pz is normalized. The 2s atomic orbital and the 2pz atomic orbital are orthogonal to each other because this one is symmetric with respect to z. This one is antisymmetric with respect to z. So the product is antisymmetric with respect to z. It's an odd function. So if you integrate a odd function from z equals negative infinity to z equals positive infinity, the result is 0. Similarly, this one is 0. Okay. By the way, this means complex conjugate. So again, this atomic orbitals, each of them is normalized. And they are orthogonal to each other. Okay, we're talking about the 2s orbital and the 2px orbital centered on the same atom. Okay, so same here. These two are orthogonal to each other. These two are orthogonal to each other. All these are orthogonal to each other. However, it's not necessarily true that a 2s orbital on one carbon is orthogonal to a 2pz orbital on another carbon. Okay, that's not necessarily true. But on the same carbon, the 2s orbital and the 2pz orbital are always orthogonal to each other. And same here, 2px and 2py are orthogonal to each other. 2px, 2pz, 2py, 2pz, they are all orthogonal to each other. So these four atomic orbitals, 2s, 2px, 2py, 2pz, are all normalized and also orthogonal to each other. So we use this information to derive the squared modulus of this hybrid orbital. And we saw the integral of the squared modulus of this side is just 1. Now let's look at the shape of the sp hybrid orbitals. So essentially, we just mix this s orbital with one of the p orbitals. All right, so this one and this one, they will be mixed. And then we get this sp orbitals. All right, over here, this is the center of the atom, the nucleus, where the nucleus is. These two are intact p orbitals. So when you have this carbon forming the sp hybridization, you have a p orbital here, another p orbital here, and then this one is a sp hybrid orbital, and then this one is another sp hybrid orbital. So we can use this sp hybrid orbital to form a sigma bond with this hydrogen. Alright? And same here, this sp to form a sigma bond with this hydrogen. And in the middle, we have this sp from the carbon on the left, this sp from the carbon on the right to form another sigma bond. So sigma bond, sigma bond, sigma bond. So 1 sigma bond, 2 sigma bond, 3 sigma bond. And also in the middle, you have two carbons, each with two intact p orbitals. I'm going to call this 2py and 2py. So 2py and 2py have constructive interference. It's called pi bond. 2px and 2px can form a second pi bond. That's why in this molecule, you have a triple bond between the two carbon atoms. One single bond and two pi bonds. We can look at another example, beryllium dihydride. So in beryllium, you have the 1s2 electron configuration. Again, you can promote one of the two s electrons into the 2p orbital. And then you have 2s1, 2p1. You mix these two and form two different sp hybrid orbitals. Well, when I say different, they have actually the same shape, but they are pointing to the opposite directions. So again, if you look at beryllium, one of the two sp orbital is pointing toward the left and form constructive interference with this hydrogen. The other one with the same shape but is pointing to right and form another sigma bond with the hydrogen on the right. The plus signs and negative signs are the faces of the wave function. They have nothing to do with the charge. Now ethane, C2H4, or ethylene. So now we'll look at the sp2 hybridization of the carbon atom. This is the shapes of the three sp2 hybrid orbitals. They have an angle of 120 degrees. So I'm going to just show you one of the three. So you have to go here and then go here. This is one of the three sp2 hybrid orbitals. All right. Now I'm going to show you the wave functions. 1, 2, 3. So the first one is made from 2s and 2pz. This one 2s, 2pz, and 2px. 2s, 2pz, and 2px. Look at the sign. These two have different signs here and here. We can also prove each of the three hybrid orbitals is normalized, and they are also orthogonal to each other. So when several hybrid orbitals are both normalized and orthogonal to each other, we say these hybrid orbitals are orthonormalized. Okay, orthonormalized. So let's prove this psi sub A is normalized. We take the integral of the squared modulus of this psi sub A, so it's here. And then we get this guy squared, we put it here. This guy squared, we put it here. There are two cross terms. All right, so the complex conjugate of this one times negative this one, and this one times negative the complex conjugate of this one. But because 2s and 2pz are orthogonal to each other, the integral of these two cross terms are exactly 0. So we just need to look at this guy squared and this guy squared. This one is just 2/3 because 2pz itself is normalized. This integral is 1/3 because the 2s atomic orbital is normalized. So the result is 1. This hybrid orbital is normalized. We can also prove this psi sub b and psi sub c are normalized. I want to show you psi sub b and psi sub c. You just need to integrate the squared modulus of this guy and prove the integral is 1. It's pretty simple. You do not have to look at any cross terms. All the cross terms are equal to 0 because 2s, 2px, 2pz are orthogonal to each other. So all you need to do is you need to get this squared, which is 1/6. This guy squared it's 1/3, and this guy squared is 1/2. So 1/6 plus 1/3 plus 1/2 is simply 1. Okay, so over here. And similarly, you can prove this psi sub c is also normalized. We can also prove that they are orthogonal to each other by doing the integral of psi sub a complex conjugate times psi sub b. So something like this. Okay, you may ignore any integrals that involve the product of two different atomic orbitals, because again 2s, 2pz, and 2px are orthogonal to each other. So basically, if you look at this, you just need to worry about this times this. Alright, so this is just 2pz times 2pz, right? So you got this term here. And then 2s, you have 2s here and 2s here, so put them here. Alright, 2px, you cannot find another 2px. So this guy times this guy, and then you integrate the product, you get 0. The integral of this guy times this guy is also 0, so don't worry about it. The cross terms are also 0. And this is 1, alright? So because 2pz is normalized, this is 1. Therefore, the result is this product, negative 1/3, plus this product, which is positive 1/3. The result is 0. Well, we can also prove psi a and psi c are orthogonal to each other. Psi b and psi c are also orthogonal to each other. Those are the detailed derivations. Now let's look at the picture of ethane. Each carbon uses the 3 sp2 hybrid orbitals to form a sigma bond with the other carbon, and also with 2 hydrogen atoms. So 1 sigma bond, 2 sigma bond, 3 sigma bond. And then each of these 2 carbon atoms has a intact p orbital, and these 2 intact p orbitals may form a pi bond. Ethane, C2H6. We'll look at the sp3 hybridization of the carbon atom. So this time we're going to mix these 4 atomic orbitals and to make 4 sp3 hybrid orbitals. If we put them together on the same carbon atom, they look like this, a tetrahedral shape. Mathematically, we can write out the functions, the wave functions, for these 3 sp3 hybrid orbitals. There are 4 of them. Okay, 4 sp3 hybrid orbitals. Those are the wave functions. So they look almost exactly the same, except for the signs. Minus, plus, 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 minus, 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 plus, minus, plus, minus, 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 plus, minus. We can easily prove these 4 hybrid orbitals are normalized and orthogonal to each other. Now I'm going to show you the bonding structure of the ethane molecule. Each carbon has 4 sp3 hybrid orbitals, and each of the 4 sp hybrid orbitals form a sigma bond. 3 with this hydrogen atoms and 1 with the other carbon. So in summary, the hybrid orbitals are simply mathematical functions that are used to explain the bond angles and the molecular structures of the molecules. Now we know in this ethane molecule, the bond angle is 109.5 degrees because of the tetrahedral structure of the 4 sp3 hybrid orbitals. In ethane, the bond angle is 120. That's the angle between the sp2 orbitals. And when you have a sp orbital, the bond angle is 180 degrees. The molecular orbitals formed between the hybrid atomic orbitals of carbon and the 1s orbitals of hydrogen in this 3 molecules, ethine, ethane, and ethane. They are called localized molecular orbitals. Alright, so I want to emphasize this. If you are looking at the hybrid orbitals centered on the carbon atom, it's still an atomic orbital. It's a hybrid atomic orbital. Only when this atomic orbital overlap with another atomic orbital from another atom, we call that molecular orbitals. Specifically, we call them localized molecular orbitals because these localized molecular orbitals are usually localized either on one bond or one lone pair. Alright, so it's localized. On the contrary, later you will learn the symmetry-adapted canonical molecular orbitals. The canonical molecular orbitals are also mathematical functions used to describe the electronic structure of the molecules, but the symmetry-adapted canonical molecular orbitals are often delocalized over the entire molecule.